Welcome to this lesson on momentum and impulse. We're going to define momentum, learn about its connection to Newton's second law, learn about impulse and the momentum principle. So let's begin with what is momentum. The definition of momentum is mass times velocity, and the symbol is a lowercase p. So this is the definition of momentum. This is a vector equation, so just as before with Newton's second law, we will have component equations, the x component equation and the y component equation. And momentum has units of mass times velocity. Typically we use kilograms and meters per second, so the units are usually expressed in kilogram meters per second. And the direction of the the direction of the momentum vector is going to be the same as whatever direction the velocity has. So let's do an example. A 5 kilogram bowling ball has a speed of 4 meters per second to the right. Find the momentum. Well, to find the momentum, we need to think about what direction is the momentum. So the ball is only moving to the right, so it looks like the x direction is all we need to pay attention to. So the x momentum equals the mass times the x velocity. The mass of the ball is 5 kilograms. And I have to think about the velocity. Be really careful with momentum because we are dealing with vectors, so signs are really important. So the speed is 4, but the velocity has to include information about the direction. And I'm going to choose that to the right is my positive x direction, so then the velocity would be positive 4. So positive 4 meters per second, and my momentum then is 20 kilogram meters per second. Part B, what is the ball's change in momentum? Well, change in momentum, I should finish reading it. What is the ball's change in momentum if a force is applied to bring it to rest? So this is going to be the v final in the x direction of 0. So change in momentum is going to be the final momentum minus the initial momentum, all for the x direction. The final momentum is the mass times the final velocity in the x direction. But the final velocity in the x direction is just 0, so this term will become 0. Minus the mass times the initial velocity horizontally. Well, this is the momentum I already found over here, so this is going to just be 20. So 0 minus 20 kilogram meters per second equals negative 20 kilogram meters per second. So this means that the momentum decreased by 20 kilogram meters per second. It started at 20, it decreased by 20, and then the end momentum was 0. Let's find a connection now between momentum and Newton's second law. So Newton's second law says that the net external force equals the mass times the acceleration of an object or a system. We are going to try to rearrange these variables, substitute things to get to a relationship that involves momentum. Because right now we don't see momentum in here anywhere. So let's begin by replacing the acceleration vector with its definition, which is the change in velocity over time. And then on the next line, if we look at this, so looking at this we can see that this is starting to look a little bit like momentum over here, mass times change in velocity, a little bit like mass times velocity. So let's multiply both sides by delta t. And that will move the delta t to the other side. So on the other side, I now have the net external force times the time interval equals the mass times the change in velocity. Let's expand this further. Change in velocity is final velocity minus initial velocity. And expanding this even further, we have mv final minus mv initial. Now here we see momentum terms. So mass times v final, that is just the final momentum, and mass times initial velocity, that is just the initial momentum. And now we see this looks like a change, a final minus an initial, so this is the change in momentum. Now I'm going to carry down the left side to complete my equation. Okay, So this is an equivalent way of stating Newton's second law. All we did was substitute in the definition of acceleration. This gives us a relationship between the change in momentum and the force that's applied. And this makes sense because if you want to change an object's momentum, you would need to apply a force over some time period. This term here is called the impulse. And we're going to take a closer look at that impulse now. So the best way to think about impulse is, well, basically it's the product of the force times the time interval. And the best way to think of it is actually as the area of the force versus time graph. So if you had a constant force that was applied over some time interval, you can see that force times delta t, well, delta t would be this part of the graph and force would be the height. So F delta t is just really the area. And the best way to think of impulse is as the area of the force versus time graph. This especially becomes important when we have forces that have changing values over time. So for example, a tennis ball hitting a tennis racket, as that ball hits the racket and the strings stretch, the force is going to increase and then the force is going to decrease again as the ball leaves the tennis racket and the strings relax. So this is the impulse. This area is basically the product of the force times the time, even though the force was changing over that whole time interval. And calculus can be used to find this area, which we'll be doing later. But for now, let's think about what average value of force would give us that same area. So what rectangle would have the same area as what's under the curve here? Whatever that value is, whatever that force is that would give us that same area for that time interval, that's the average force. So impulse can be expressed in terms of this average force. The symbol for impulse is capital J, and we can express this as the average force vector over the time interval. This is a vector equation. So we have the horizontal component is the horizontal component of the average force times time, and the y component is the average force in the y direction times the time interval. I'm just not writing average to cut down on my subscripts, but these are still average forces. The units of impulse are newtons for the force and seconds for the time. And we might wonder, well, newton second, how does that relate to our units for momentum? We had kilogram meters per second for momentum, and we're going to have newtons times seconds on this side. Like, are these equal? Let's check it out. So a newton is a kilogram meter per second squared times the seconds, and so one of the seconds is going to cancel out in the denominator, and we'll have a kilogram meter per second left over. So it does have the same units as momentum. Let's do a little example. The bowling ball from example 1 is brought to rest by applying a force that has a magnitude of 10 newtons for 2 seconds. Calculate the impulse on the ball. Well, the ball is moving horizontally with this velocity. To stop it, we're going to need to apply a force in the other direction. So thinking about signs, I can tell right now the force is going to be negative. So my force is going to be negative 10 newtons. See how you have to add the sign on your manually. And the time is 2 seconds. So let's find the impulse. The impulse in the x direction is the x force times the time interval. And the x force is negative 10 newtons. The time interval is 2 seconds, which gives us negative 20 newton seconds for the impulse. A negative here means that the force was negative, so it means that the impulse was acting on the object in the negative direction. What other combination of force and time interval would provide the same impulse? Well, you notice that impulse is force times time. We had 10 times 2, giving us 20. Well, what other forces and times could you multiply and get 20? What if we had a bigger force, so 20 newtons in the negative direction? It would have to act for 1 second to give an impulse equal to this. Or what if you have a smaller force, maybe -5 newtons? It would have to act for 4 seconds to get to -20 newton seconds. So you can see that to get the same impulse, you could have, for example, here, a large force multiplied by a little time, or here we had a small force multiplied by a large delta t. The momentum principle is going to be very useful in applying momentum and impulse to problems. So we're going to take this result we got from Newton's second law and just expand it and rearrange it a little bit. So starting with sum of the forces times the time interval equals delta p, I'm going to expand out the change in momentum. So change in momentum becomes final momentum minus initial momentum. And then I'm going to add the initial momentum to both sides of the equation. So adding initial momentum to the right, adding initial momentum to the left, what I get is initial momentum plus, actually, let's just change this to impulse. This right here is the impulse. So plus the impulse equals, and these have gone away, equals the final momentum. So this is our momentum principle, and it says that if you start with some initial momentum, and then the object experiences an impulse, that's going to change the momentum to a new final value. And then you can also see if this impulse is 0, that the initial momentum equals the final momentum, and that is going to be very powerful because it helps us deal with situations that have very messy, complicated forces. And if we can set up our system so there's no impulse on it, no net external forces, then we can have the conservation of momentum. It would stay constant. This is a vector equation, so once again we have that the initial x momentum equals, the initial x momentum plus the impulse in the x direction equals the final x momentum, and then for the y direction, the initial y momentum plus the impulse in the y direction equals the final y momentum. Let's apply what we've learned to an example. Example 3, Justin Case is sitting at rest on a skateboard. Combined mass of Justin and the skateboard is 65 kilograms with a 4 kilogram bowling ball in front of him. He pushes on the bowling ball with an average force of 8 newtons for 1 second. Assume friction is negligible. Draw velocity vectors on the before and after pictures. Draw force vectors on the event picture. So the beforehand, it looks like everybody's at rest. So velocity of the ball equals 0 and velocity of Justin and the skateboard equals 0. Afterwards, what's going to happen? If he pushes on the ball is going to be moving to the right afterwards. And when he pushes on the ball, Newton's third law says the ball pushes on him, so he and the skateboard will be moving to the left. Draw force vectors on the event picture. Okay, the event is when the impulse is occurring, so when the forces are happening that are causing this change in motion. So let's see, Justin and the skateboard. We've got force, let's say normal force on Justin and the skateboard. We have force of gravity on Justin and the skateboard. And then we have on the ball, we have a normal force and also force of gravity. And then Justin pushes this way on the ball, so this is the force of Justin on the ball. And then by Newton's third law, there must be an equal and opposite force of the ball on Justin. I'm just going to call that Justin and the skateboard. So these are the forces occurring. Number 2, for each different choice of system below, find the impulse on the system, the final momentum of the system, and the final velocity. Draw a momentum bar chart. So in A, the system is just the ball. So here's my system, and we need to know if there's a net external force because that is going to be important for determining if there's an impulse. So looking at the ball, our external forces, that's forces caused by objects, interaction with objects outside the system, is going to be gravity normal and the force of Justin and the skateboard. Now, is there a net external force? Well, gravity and normal are balanced out in the vertical direction. So there is an external force, which is this one. So yes. Is momentum of the system constant? So the momentum of the system will be constant if there is no net external force. So if there is no net external force, then there's no impulse, and then the momentum will be constant. But if there is an impulse from a net external force, then the momentum will not be constant. So no, it will not be constant. So now we need to find the impulse and final momentum and final velocity. So to find impulse, impulse equals J. We have the x direction going on here, so we need the average force in the x direction times the time interval. So the average force on the ball is the force of Justin and the skateboard on the ball times the time interval. What is that force? It is 8 newtons. And then I want you to think, is it positive or negative? This is positive because it's to the right, and I'm defining the right as my positive x direction. This force, the ball on Justin and the skateboard, would be negative 8 newtons. So for the ball, it's positive 8 newtons. And the time is 1 second. So the impulse is positive 8 Newton seconds. So we have an impulse on the ball, so we would expect that its momentum is going to change. So it says find the final momentum. So the initial momentum in the x direction plus the impulse in the x direction equals the final momentum in the x direction. The initial momentum was 0 because the ball was at rest. So the mass of the ball times the initial velocity of the ball, which is 0, gives us 0 for that. The impulse is 8 Newton seconds. And then we're looking for the final momentum. So here's our answer. The final momentum is positive 8 Newton seconds. Okay, and let's check and see if it makes sense. The initial momentum was 0, then it changed by the impulse amount, which is 8, and so that gives us a final value of 8. And now we need to find the final velocity of the ball. Well, momentum is just mass times velocity, so I'm just going to continue here. So mass times final velocity equals 8. And the mass is 4 kilograms for the ball. Maybe I should put that this is for the ball. And dividing both sides by 4, I get that the final velocity of the ball is 2. Let's see, this is going to be meters per second. And you can work this out just to check the units, that a Newton second divided by a kilogram is a meter per second. And this is positive, which matches what we expected. So the velocity of the ball afterwards is positive 2 meters per second. Our last task for this part is to draw a momentum bar chart. So a momentum bar chart is going to show all the parts of this equation. It's going to show initial momentum, impulse, and final momentum. So initial momentum goes first, then the impulse goes in a little dashed rectangle to show that it's the thing causing the changes, and then the final momentum goes to the right. So positive is up, this is 0, this is negative values. The initial momentum was 0, so please when it's 0 indicate that it's 0 by drawing a little 0 line and writing a 0. The impulse was 8, so that's positive, so like a little bar in your bar chart, and this equals 8. And then the final momentum was also 8. So it's sort of like we're doing some accounting, some momentum accounting here. We started with 0 for the initial momentum. It changed by 8 because of the impulse. So 0 plus the change equals the final result of 8.